All right, hello. And today we're going to be doing volumes of solids part one. Okay, this is part one of a three-part series. So volumes of solids is long. In this video, we'll be talking about, how to find volumes. Next video, I'll be doing how to find volumes of rotated areas, right? Rotating around an x-axis or the y-axis or any axis of rotation. And finally, in the third video, I'll go over the method of cylindrical shells. So we'll start with the basics, volumes of solid. We're going to be using the slicing method in this video. That is, we have this theorem, Fubini's theorem, that tells us if we have a 3D solid, all right, we have three dimensions, x, y, and z, right? And if we have this solid, right, and we have two bounds, if we can find the area of the cross section at any point x, right, as a function a of x, right, we notice kind of how these planes are all parallel to yz, the YZ plane, kind of, if you know what I'm saying, right? And this thing is the cross section. If we can find that area, right, as a function, then we can accumulate it and integrate it from our bounds to get the volume. So the volume is just an accumulation of the area. And that is a very important fact that we're going to use. For example, all right, let's say we wanted to find the volume of a right rectangular cylinder. Now you should know the formula is pi r squared h, but how do we get it? Okay, so first we're going to have our XYZ plane. We're going to have a circle, right, at the or centered at the origin, and then we're going to go up h units on the z-axis, and that's going to form our cylinder, right? Now, we have pretty clearly that we're going to say we have radius r, height h, and that's actually all we need, right? And if we want to find this volume, our number one, our key point is to be able to find the function that gives us the area. Now, in this case, if you take any cross-sectional area that's parallel to the base, obviously, we're gonna have that it's a constant area, right? Since clearly it is just a cylinder, no matter how we cross it, this area is the same anyways. So we're gonna put this right at z. We don't know what z is, it's a random point, so we have a function, right? At z, the area of the cross-section perpendicular to the z-axis is given by a of z is pi r squared. The z doesn't matter, it's just a constant anyway. So, Fubini's theorem tells us that we can find the volume of a cylinder of height h and radius r by, as a function of h, right, the integral from 0 to our height of a of z dz, which is the integral from 0 to h of pi r squared dz. And by the way, dx, dz, dy, same thing. As long as the area and the variable of integration have the same variable, then we're good. And of course, if you know how to integrate, that's pi r squared h. So that's how we might get our formula, right? So as long as we can find for any z, right, or this maybe we have an x, we can find this area function, we can integrate that and get our volume. Now, example two actually has a dynamic situation, right? The volume of a right circular cone with height h and radius r. We're going to put the vertex of the cone at the origin, and it's going to be increasing in height, and its radius is also going to increase. Now, you may remember kind of from related rates, what we're going to be using similarity. All right, we're going to take any height z, all right, and we have this triangle. We have similar triangles here. This is r of z, it's the radius and as a function of z. This is r and this is h. By similarity, we have this relation. And of course, we can solve for r of z by multiplying, and we get, believe it or not, a linear relationship, right? So our radius is now a function of only z. Why do we want that? Well, the reason why is because in order to find the area, we need the radius. And in order to find the volume, we need the area function. But it has to be a function of z or x or y, whatever variable we're integrating in respect to, we need that as a function of whatever. So at z, the area is pi r squared of z, which is pi r squared z squared over h squared. So if we integrate from 0 to h, which is our bounds, then we get our volume. v of h is the integral from 0 to h of a of z, which we can, factor out this constant, right? Z squared becomes z cubed over 3, and the second fundamental theorem of calculus from 0 to h. And then we're going to ignore 0 because if we plug in 0, that's minus 0. But if we plug in h, we get h cubed over 3. The h and the h squared and the h cubed cancel out. You just get 1/3 pi r squared h. And you may actually recall this. That's how we get the formula, right? 1/3 pi r squared h. Next example is a sphere, and this one's gonna be a bit more like difficult, so be sure to pay complete attention to the steps here. We're going to center our sphere at the origin, right? If that makes sense. That's our center. We're gonna go on the x-axis up to some point r, and then on the other side on the x-axis to negative r. Capital R is our radius, okay? Now, we're going to take for any x now, and this time we're integrating in respect to x. We're going to take at any point x, right? We're going to consider this cross-sectional area. The cross-section of a sphere is a circle, all right? So if we can find this radius as a function of x, then we can find the volume, right? We can find the area function. We're going to also consider the great circle, I believe it's called, right? This circle right here, which is perfectly in the middle, it intersects this cross section at this point specifically, which is where we'll consider, all right? The reason why is because we're considering here, this is where z is 0. This is the sphere for when z is 0. If you want to convince yourself, plug in z is equal to 0, and you'll just get the equation of a circle centered at 0, comma 0. So this point specifically has to be with an x coordinate of x, right? That's what we're considering. And it has to have z coordinate 0. So of course its y coordinate is just y, right? And now the reason why we want to consider that is because we want to forget about z. And we're just going to get that x squared plus y squared equals r squared, or the absolute value of y is the square root of r squared minus x squared. And how are we going to use this? Well, this radius r of x is just the y coordinate. If you notice, if we just create this construction, you'll notice these two are, equal. So if we can find this y coordinate, which is what is we're looking for, we have the radius. Now, we do have the y coordinate. Here's a function. Now, of course, we do have to make sure that it is the absolute value, but that issue gets resolved because we're going to end up squaring it, as you'll see. So what do we have? At x, the area is pi r squared of x, but r of x, which is the absolute value of y, right, is just the square root of r squared minus x squared. So now that we have our radius as a function of x, right, r is a constant, we can just write this, which is the square root and the square cancel out, pi times r squared minus x squared. So the volume, right, which changes with r, it only changes with r, right? It depends on our choice of a radius, is equal to, we're accumulating from negative r to r, all of the cross-sectional areas. So the cross-sectional area is pi r squared minus x squared. We factor out a pi, we integrate, right? We do some arithmetic, and we get our solution is 4 pi r cubed, sorry, 4/3 pi r cubed when you're doing the arithmetic, right? And that gives us our formula for the volume of a sphere. You may have known it, but that's how you derive it using calculus. So now that we have some experience with some examples, let's do a 2015 AP Calculus, a BFRQ. This is a calculator question, so get your calculator ready. Let f and g be the functions defined as followed, right, as it shows. Let R and S be the regions enclosed as shown by the graph. Now, the question is, region S is the base of a solid, right? It's not, the region S is a base, right? And the cross sections of the base, which are perpendicular to the x-axis. So it's going to be something like this. I don't know. This is kind of what it's going to look like. I don't know yet, but it says all the cross sections are squares. Find the volume of the solid. Well, let's try to make a three-dimensional figure representing it, right? And obviously on the page, and we won't have time for this, but you should be able to visualize it in some way. Now, this is what it looks like in X, Y, and Z. And this is the cross section. It's a square. We're going to choose some arbitrary cross section. If we want to find the volume, we need an area function. So we're going to pick any X, right? Any X we want to pick here, and we want to take any square, and we want to find that area, right? Here, I constructed some other collection, a collection of cross sections so you can kind of visualize how it's increasing and decreasing as we slide around our value of X. Now, what do we have up here? Well, we need to first find this. This gives us our area. Why? Well, the area of the square is just this side length squared. And this side length is a vertical length of S, right? And if you know from area how to find the vertical length, it's the absolute value of F minus G. F is above G, so it's just F of X minus G of X. So our vertical length is F of X minus G of X. The area is the vertical length squared, right? So this is our vertical length. And finally, if we just want to find the volume, we need the lower bound and the upper bound, and we need our area function, which we now have as VL squared of X. So now it's time for our calculator, all right? So we need to find C, right? That's where they intersect right here. That's where I said C. So we're in our calculator. We are going to try to solve for when f of x, which you should have defined, right? Hopefully you defined f. So here's a little tip. All right, we're going to define f of x in our calculator so that we don't have to rewrite it again. And as we're doing this, we're going to be sure to put everything exactly as is shown. We don't want to mess up and accidentally put something that's not there. Otherwise, our entire solution is going to be wrong. So we've defined f, and we're going to define g. And what this is going to give us is that we're going to plug in, well, now that we have everything written down, we just plug it into the calculator, and it's a very easy problem from there. So we have our f, and we have our g, and we want to find where f and g intersect. In this case, we'll just solve for when f of x is equal to g of x, and we don't have really any restrictions on x. Hopefully, it shouldn't be an issue. So we clearly get x is equal to 0, x is equal to 1.0328, x is equal to 2. Okay, yeah, this x is equal to 2 is kind of obvious. So c is equal to that number, all right? So let's write it now. C is equal to 1.03283. This is from our calculator, all right? And that's going to, now we can plug that in. We're going to now finally plug in from C, which is 1.03281. No, 1.03281 to 2, right? Because those are bounds. And what is our A of x? Well, we already specified that that's the vertical length squared. Vertical length is f of x minus g of x, so we're going to write f of x minus g of x squared dx. And that gives us our wanted volume, which happens to be 1.28316. So that's a volume of this solid formed. And they love to ask square, square, square because it's a simple figure, doesn't require much thinking, but it tests your knowledge. So you do need to know that in order to find this, you need to find the cross-sectional area. You need to integrate that, and you can get your answer. And the rest is just a calculator. So hopefully this collection allowed you to kind of visualize how the square moves as we change x and how that forms a solid. But if not, I highly encourage you to search up if you have access to College Board videos, for example. They have the actual solid and they will show you in 3D. Or if not, search it up and it'll definitely help you get a better intuition for the figure. So hopefully you found this video useful. And if you did, definitely watch my other videos. And in the next video, I will discuss revolving, right? Solids formed by revolution around an axis of integration. So good luck.